Okay, everybody, welcome to this afternoon seminar. We are lucky today to have Professor Chus Sanz-Serna from Universidad Carlos III of Madrid to speak to us about numerical integrators for the Hamiltonian Monte Carlo method. Please, Chus. Thank you. 45 minutes.
Yeah, so first of all, I'd like to thank the organizers of this semester, and in particular, Ari, for inviting me here. My stay here has been very fruitful, and I've done a lot of work, and I've enjoyed myself, and I hope the same applies to all of you. And I also thankful to Elena and Brynjolf that are always very kind to me, and they asked me to give this seminar. Now they asked me at a very short notice, so I decided it was best to recycle a seminar I had given before, rather than preparing anything new. And by looking in my computer, this is what it came more readily. So the research I'm going to be reporting here is joint work with Sergio and Fernando that are there, then with a bunch of people at the Basque Center for Applied Mathematics, Elena Ahmaskaya, Mario Fernandez Verdas, Diana Radivojevic, who is from Serbia, and Nawaf Bourabi. And this talk, those slides, when I prepared them, they were really prepared to be presented to an audience of statisticians. But don't worry, I mean, I will give you a few elements that hopefully will let you follow and understand what I say, but I will not go into any details of the statistics, and in any way, I don't think they are really needed to understand the main ideas in this talk. So the problem is that in RD, D could be very high, could be thousands or even tens of thousands. One has a probability distribution function, so that no locations in RD are equally likely, and one aims at obtaining samples of this distribution. So this task is, of course, very common in statistical physics, where I say to find possible configurations of a molecule, you have to obtain samples from the so-called Boltzmann distribution, and so this is very common. But it's even more common in statistics, because in statistics, nowadays most people use this Bayesian approach, and in the Bayesian approach, the distributions that you have to work with vary with your problem. So it's not the case that, as when I was student, that we had the tables for the normal distribution and the chi squared and chi squared in English, and so on and so forth. No, this time, each time an experiment is performed, according to the data that you get a new distribution. Those cannot be tabulated, they cannot be coded in MATLAB, and then the only way to use them is by obtaining samples of a distribution like this. And in fact, Bayesian distribution only became popular and useful once computers were available to obtain those samples. It also obtaining those samples, like Monte Carlo technique, is probably one of the main uses of computers nowadays, just like solving linear systems of equations or performing fast Fourier transforms, things like this. So this task is in this big category. So there are many ways in which you could obtain samples from this function, from this distribution, but one that has become extremely popular in the statistics literature in recent years is what the statisticians call the Hamiltonian Monte Carlo method. And for my talk, it's very important to realize that this Hamiltonian Monte Carlo method is used a lot. It's an expensive computation, but maybe 99% of the expense of this computation is in integrating a system that should be well known to the audience, this system of Hamiltonian differential equations. So in practice, what everybody does is integrate the dynamics by the Verlet or the Stirner method that is well known. We have a kick, a drift, and a kick. This is obviously a splitting integrator. So one step is performed by this map or affected by this map psi, where you first flow with this B part, which is just taking into account the kinetic, the potential energy. Then you have this drift, which is flowing with this partial system, and then you close the step in a symmetric way with this B. So this is what people use in practice, and it's very important for the use of this method to notice that this map that advances the solution is over one step or over many steps, doesn't matter, has some properties. One of them is volume preserving, and the other is that is reversible due to this palindromic structure, a half, 1 1/2. And those properties are essential for the sampling because they allow for a simple accept, reject rule. And maybe at this point I will interrupt the flow of my slides and I'll give you a little explanation in this blackboard. So we are in QP space, and the way the algorithm works is that you are at some location. This means that you've got a sample here of your distribution. You're taking the Q component, you've got a sample of the distribution, and then you let it flow with your Hamiltonian system. And then, so you come here. It's very important for the sampling to notice that this point can be very far from this one. So this is what really makes the algorithm appealing, because it can decorrelate your samples. You can have one sample now, the next sample could be very different from other samples, which is not the case for other Monte Carlo technique. So you come here and then you record your Q value. And now once you found this Q value, the rules of the game is that you not always accept it. So what you have to do is to compare this is the energy at the end, and this is at the origin. So this is the final point, it is the origin. So if this is more than 1, so that you've really lost energy, that's okay with you. And this value of Q will be your next sample. This is because really we want to obtain samples for e to the minus h, and if we're given the opportunity to move to a location with a higher probability than our current location, we will use this opportunity. So I'm here, so this carries a probability. If I'm given by the numerical integration the opportunity to go to a location that is more likely, then I will go there to enforce this. Now what happens if I don't get acceptance? Because when I integrate, at the end of the integration, my energy is higher. Well, then I have to make this ratio and say if this ratio is 50%, this will mean that 1 out of every 2 that I'm at that predicament, I will go to the end, and 50% of the time I'll stay put. Okay, so if I gain energy, sometimes I stay put, and sometimes I go to the final destination. This is in case of rejection. Now, what's the purpose of this? The purpose of this is that by some black magic, this guarantees that with no error, the samples that I generate are samples from the distribution I want to sample from. Okay, so this accept reject mechanism is very clever because introduced by Metropolis and his co-workers in 1953, and is the key thing because it guarantees that I can sample from any distribution, no matter how complicated. But of course, you see, if I integrate and I get a rejection, then I've wasted all my computational effort. I mean, I've sampled this potential many times and the gradient, and then I don't use the final point. So rejections are not welcome because they are a waste of computational effort. Okay, now again, I get a rejection if my energy error is big. So if I gain energy and I'm offered to go to a distant destination with more energy than my current destination, of course this, I don't need to point out to this audience that this energy error is only due to the Fairley time stepping, because the exact Hamiltonian dynamics will conserve exactly energy. So this is due to numerical errors. So so this is the thing. So I think, is this clear? Shall I repeat or give any additional explanation? So that this goes down. And now the slides have disappeared. No, but they're back. Fantastic. So the purpose of this talk is to discuss whether what people are using, this Fairley algorithm, is really the best that one can use. And then before we choose an integrator, we have here 3 points. Well, it's not written there, but it's very important that the integrator has to be reversible and volume preserving, because otherwise this accept-reject mechanism doesn't work. So, but given that I restrict my attention to those integrators, here are the following points. First of all, we are only interested in energy errors. So we don't care so much if when I integrate, I get slightly farther or maybe shorter, provided that I don't make an energy error. So phase errors are completely irrelevant. I couldn't care less about them. Then the thing is that high accuracy is not required, because according to the recipe for computing the accident probability, even if you make an energy error of 1 unit, yesterday we saw those errors, they were 10 to the minus 8, 10 to the minus 8, even if your error is 1 unit, you still accept with probability larger than 36%. And even if your error is 2 units, then you accept with probability 13%. That is not too bad. It's not ideal, but it's not too bad. Here there's a caveat, and this is that, of course, energy is an extensive physical magnitude that adds across degrees of freedom. So if I have 1 or 2 degrees of freedom, integrating this with 1 unit energy is I mean, one could even concoct the solution by thinking without any numerical method. But if you're in a problem, as you often are in practice, where you got, say, 5,000 degrees of freedom, then this means that per degree of freedom, you have to allow errors of 10 to the minus 3 or 10 to the minus 4. So the task becomes more demanding as the number of degrees of freedom increases. And then the other thing is that it's very important, and this is maybe a bit unusual, that the sign of the energy error matters. If I lose energy, that's all fine. I will accept 100% of the time. It's only if I gain energy that I'm not happy with that. So maybe you can think that one could have a method that always decreases energy. But then this figure is very, very important for what follows. The fact that we are dealing with schemes that have to be both volume preserving and reversible has a big impact on your energy errors. And this is in this figure. So Q naught, P naught is your initial condition. And then just imagine that you integrate and you go to that point Q star, P star. We've increased energy, because we are at an outer energy level, and we are not happy. Maybe we get a rejection. But because the scheme is reversible, if I started from there, I go there with a decrease in energy of exactly the same amount. So in phase space, to each point with an increase in energy, there's a point with exactly the same increase or decrease. So it's not possible to always have decreases. Sometimes you increase, sometimes you decrease. And also because you preserve volume, if rather than looking at the point, you look at the neighborhood, you see that integrating over these neighborhoods, the average increase in energy on top exactly equals in magnitude the decrease on the bottom. So there's a big symmetry here. So in fact, if one would be interested, and here averaging things with respect to the standard Lebesgue measure, the PDQ, then on average your energy error would be 0. Now here is different because the distribution we are sampling with is between -h. So we really, as I told before, points with a lower energy have more weight. This means, this means that when I perform the average, the upper thing that starts from lower energy is more likely than the lower thing. So I'm more likely when sampling to find the point Q0, P0 than this one. So the cancellation is not complete, but there's a lot of cancellation. So this is a geometric argument that I like, but if you don't like it, then you can perform some integrals and changes of variables, and you came to the same thing. And this means here, this is the whole thing. This is the expected energy error. So I'm displaying, I'm sampling, okay? So this is random variable because I'm now here, later there, and I average. And at each point I perform an error. But on average, I have this bound. This is the PDF I'm sampling from. And you see that this is the pointwise energy error, which really means that when I'm performing this task, on average, my scheme is of twice the order that people realized before looking at this. So there's some magic here. So, so far the conclusions is that for volume preserving and reversible integrators, the error energies are on average much smaller than one would think. So people say, okay, Fairley is only second order. It's not true. It's fourth order for this particular applications. Then the asymptotic properties of the scheme as h goes to 0 are not relevant because those schemes are operated in practice with such large values of h where the information that you derive from a Taylor expansion is not relevant. So you should analyze your things for fixed h. But then, if you're a numerical analyst and they tell you to do some analysis without the Taylor expansion, then you are in big trouble. If in the ODE community, either you Taylor expand as delta t goes to 0, or else you have to look at a model problem like y prime equals lambda y. So, according to this, when Sergio Fernando and I started this paper we wrote, we said, okay, we want to look at the model problem, we want to look at large delta t, and keep our fingers crossed that the methods that we derive for this model problem are still relevant, just in the same way that, because you know that the backward-Euler method is good for y prime equals minus lambda y, with a lambda very large, it will be good for other stiff problems.
Can I just ask you on the previous slide, presumably another nice thing is that the sign of delta doesn't matter because it's squared, it doesn't impact on the E of.
Yeah. So, thank you. So the model problem here suggests itself is the harmonic oscillator that in probability corresponds because it's e to the minus v corresponds to the univariate Gaussian distribution, so the well-known bell, and the true solution over time t is this rotation, and when you use a method, assuming that is linearly stable, then the evolution is changed into something like that. So you see that there are two things in this matrix. You can express it in terms of this theta and this chi. So theta governs the phase error, which is here completely irrelevant, and this chi really governs the energy error. So if we found a method where chi of h is 1 for all h, that would be ideal for us, because at least in the harmonic oscillator, we would get no energy error, would move exactly in circles, okay? But from this chi, you can take it further, and then you can derive this bound for the average energy error. So for each h that you are using for the harmonic oscillator, then the error is always positive and an average, and is bounded above by this quantity rho of h that you compute in terms of the chi. So for each integrator, you compute the chi for h, and then this gives you an upper bound of the energy error. And of course, if chi was 1, then rho would be 0, and you get zero error. As an illustration, look at the Ferle method. If you do this for the Ferle method, you get this bound by computing the chi function. Of course, as h goes to 2, which is the upper limit of stability, then the bound blows up, which you expect, but at h goes 0, you see this factor h to the 4th. The method is 4th order. Okay? So even if h is 1, which means that in the harmonic oscillator you only put like 6 points along a circle, then the expected energy in error is only 1 divided by 24. And recall that before we were happy with errors of 1. And then if you have h, then the expected error is less than 1 over 480, so this is very small. This is not factorial, unfortunately. Well, this is only for the harmonic oscillator, but just as the standard stability theory that you derive from y prime, because lambda y applies to all linear constant coefficient problems, this applies to all Gaussian distributions. So if you have a Gaussian distribution in d variables, no matter how large the d, you have this bound, you have to compute this rho, and h is the delta t that you are using, and omega is the frequency. So that h omega is like a non-dimensional combination. You have to take the rho over all degrees of freedom. This is completely general. It doesn't require that that is diagonal or anything like that. So even if there are correlation between the different variables, this would be the case. So now, how do we improve on Ferle? So something that suggests itself is to use splitting algorithms. Ferle is ABA, but you could use a more complicated, more sophisticated kind of a splitting. And here, it's very important that if you have a code written for Ferle, hopefully you could adapt it easily because it's just a matter of really changing your delta t when you implement it. This is essential. For instance, I will tell you later, this has been implemented in big molecular dynamics code. And there, it was maybe a little of a pain in the neck to incorporate those more sophisticated integrators. But this small change is already a lot of work for a big real-life code. If you move to other things, like other symplectic or Runge-Kutta or exponential is beyond what's doable. So of course, in the past, very many people have looked at various combinations of splittings to improve on this. But invariably, they based their analysis in things that will not do for us. For instance, by trying to have a Taylor expansion in parts of delta T of the energy area and trying to knock out different coefficients and so on. If you do this, you get methods that if H is very small, they perform better than Bernoulli. But here there's no point in that, because if your acceptance probability for one delta T is already 98%, you don't want to decrease your delta T, and it's really no difference to you if your errors are 10 to the minus 2 or 10 to the minus 6 or 10 to the minus 9, because it has very little impact on the acceptance. So the criteria that we decided is as follows. So this is the h-axis. So this is the non-dimensional step length. So it's really the delta t in physical units multiplied by the omega, by the frequency in the problem. And then we fixed a value h bar that I will describe later. And what we want is that our method is stable at least between 0 and h bar. If that is the case, we don't care about if it's stable here or there, so we are not trying to increase the stability region to have it very long, like kind of Chebyshev or anything like that. This is not our game. So what we're going to do is we have a class of methods, this is fixed, and for each method we've got a raw function. And we want to identify the method within our class for which the maximum of a raw function in this interval is as low as possible. Okay? So it's not putting attention when h goes to 0. It operates in a long interval. And then how do we choose this h bar? Well, experimentally we found that for Verlet, a reasonable range of step sizes, non-dimensional step sizes, is from 0 to 1. For stability, it can go from 0 to 2, but if we have many degrees of freedom, then maybe 1.5 was too big. We thought that between 0 and 1 was reasonable. Then we argued if with Verlet we can have h between 0 and 1, and our integrator uses the R evaluations of the force per step, we'll ask for a method that operates well between 0 and R. Okay? So that it can be competitive with Verlet. So we have to factor in the computational effort. So, for instance, if you take schemes that are palindromic, you have that thing here to be consistent. There's one parameter, this b, and for the particular value b equals a quarter, this is just a concatenation of two Verlet steps of length h over 2. So all methods of that family are second order accurate, and the one with the least error constant has b equals 0.19. So Verlet has b equals 0.25, this has 0.19. Incidentally, this number 0.1932 was first identified by Robert McLachlan and has been discovered a zillion times by different people in different communities. And so as you increase b from 19 to 25, the algorithm gains in stability. The stability region becomes longer, but it becomes less accurate. But this is not relevant for us. What we do is to minimize the maximum value of rho between 0 and 2, because we used two evaluations here. This leads to an optimal choice that is 0.21. So the darker line, so in the vertical axis, there's this rho that governs stability. The horizontal line is the non-dimensional step size. The darker line is Verlet, and this more gray line is the method we are suggesting. So you see that if you restrict the attention for h between 0 and 2, this method is much better than Verlet is below. If we were interested in larger values of h, then Verlet is optimally stable, so it's stable up to 4. So the black line would asymptote to infinity at 4, whereas the stability of our method is more limited. The asymptote is, well, it's almost what you see there, so it's already growing very quickly, but we don't care. Okay? So you see that here, probably the largest difference is when h equals 2, or maybe that other part, but since this is logarithmic, you see that this is a factor of 100, almost. Well, you can play the same game with 3 evaluations, and this is more difficult because of stability considerations and so on. But here is what you have. This black is Verlet, and this is the new method, and you see that the difference here is maybe 3 orders of magnitude. Okay. So this means that for a Gaussian target, those methods perform much better than a Stirner, leapfrog, Verlet. Of course, we don't want to sample from a Gaussian because this is automatic in all environments. We want to see how this extends to real-life applications. Yes, like in all these, you derive your method looking at y prime equals lambda y, but then you want to apply it for more things. So this example here is an alkane molecule that has 27 degrees of freedom. So this is the Boltzmann distribution of this to find the configurations of this alkane. So this is of interest in statistical physics, and it's also a bit biased against our algorithm. First of all, because, as I said, we expect that the advantages of the algorithm becomes more marked as the number of degrees of freedom increases, right? So, because if you have 2 or 3 degrees of freedom, you use Verlet and you have the solution. So here the dimensionality is very low. So if we were to go to bigger molecules or to problems in statistics with more variates or more degrees of freedom, then that would be better for our algorithm. So this choice of test is biased to favor Verlet. Also, this alkane is very far away from a Gaussian. A Gaussian is a unimodal distribution where those molecules, of course, are multimodal. There are many stable configurations of the molecule. The molecule transitions from one to the next. So this is quite far away from a Gaussian model. In addition, we choose the delta T that was optimal for Verlet. So we simulated this molecule with various delta T, and we kept the one that is optimal for Verlet, not the optimal for our method. And you see, for the 3-stage algorithms, for these 8, then on average you accept 77% of the time. If you use a 4th order method, that is well known due to Yoshida and Suzuki and other people, so these people make it higher order, then acceptance is 0, so we don't generate a single sample, and with our algorithm the acceptance is 96%. This sigma is the standard deviation, as we make many experiments for this. So the advantages are really clear, and I could show you more examples from their previous applications. This is from molecular dynamics. And
Do you have an explanation of why the fourth order method never accepts? That seems surprising.
The deviation is zero.
yeah, because of course, if I were to choose rather than 8 femtoseconds, half femtosecond, then it would be the energy errors would be much smaller than with the other algorithms, and it would accept 100%.
Oh, okay. Because,
But I don't want
because
to
for
operate
large H,
that's
it's
the
much
machine.
worse. Because
Yeah.
fourth order. Oh, yeah, okay.
Yeah, we invest our degrees of freedom, like in a minimax or Chebyshev thing over the whole interval. Whereas to derive that method, you just look at essentially at the neighborhood of zero. Well, I'm about to finish because I have to finish now.
We have about 10 minutes or something.
Okay, good. I will. So this has been developed at the Basque Center of Applied Mathematics to this approach that is called AIA. It's the adaptive integration approach. So here the methods are derived if you have, say, 3 stages between 0 and 3. And then you think that this 3 is good, and then you derive the method, the coefficients once and for all. But here in this approach is a bit different. So here the user chooses delta t according to the computational budget. Okay, if it's a very big problem, then maybe she figures out a way. I want to use 20 femtoseconds for a molecule because I want to simulate for a long time. So this delta t has been fixed. Okay, so this delta t, then one multiplies the delta t, that is a dimensional time step, with all the frequencies that are in the problem, and then you get all the values delta t omega, and then one finds h bar as the smallest interval that will contain them all. So this means that the parameter is adjusted to your problem, to your frequencies, and to your delta t. So maybe for a problem with 6 degrees of freedom, we've got maybe something like this. Then we will take h bar to contain and then maximize. So this idea has been incorporated in this Basque Center for Applied Mathematics to this big molecular dynamics problem, GROMACS. So GROMACS, as the standard version of GROMACS, the user supplies a delta t, and then before the simulation starts, GROMACS comes back with a message that tells the user, no, this delta t is very big for your problem, don't attempt it, because you are going to get garbage. The way GROMACS decides that this is very big is because it has its own means to estimate the frequencies in the problem. So in any case, the standard GROMACS estimates those frequencies. And in the standard way, estimated, the user gives delta t, and then GROMACS says, okay, your delta t is okay. At the other extreme, it tells you, no, I cannot apply this delta t because things are going to be unstable, and there's an in-between regime where it gives you a message. Well, I'm going to run this, but maybe the results that I produce are garbage because your delta t is too big. So there's those through regimes. So now, after this modification, what GROMACS does is, if delta t is very big, so that no method can integrate with that delta t, it will say, okay, this is too big. But if there's at least one method that can be applied successfully, then it will identify automatically the one with the best coefficient to minimize the rho function. Okay? And this is the final slide. So the vertical axis is the acceptance probability. The circles are Verlet, or the Sturmer Verlet. So you see that this is a method that was derived in the US by minimizing some error coefficient and so based on a Taylor expansion. So you see this method, even though it's much better than Verlet for H small, it cannot really operate when you are here where Verlet operates. This is simply because Verlet has a very long stability region. Okay, so this one is worse. The one I've been describing by BC's Blanes and Casas, and is the one with squares. So you see that before it's like this, it can operate until the very end, but if delta t is very large, this fixed parameter scheme is worse than Verlet. So it only takes over there where it's there. And then the triangles are this adaptive. So this is automatic. The user doesn't choose anything other than delta t. If delta t is 20 femtoseconds, so those points coincide the triangle and the circles. This means that automatically GROMACS has picked up Verlet because it has decided that this delta t is very big for the problem at hand. Stability is the main consideration. Other methods are not so good, so it picks Verlet. But as if the user wants to use a smaller delta t because it has more computational resources or whatsoever, you see that then the squares, the triangles really are with the squares. So they move in a seamless way from Verlet to the other algorithm that I showed. Okay, so this is I should finish because I think I've got 1 minute for one comment. Here I've explained everything in the context of Markov chain Monte Carlo. You have this accept reject. So I've been trying to use the acceptance rate of the scheme as a matrix. But of course this applies to simple molecular dynamics. So even if your simulations don't have an accept reject rule, yeah, it's good for your simulations to use this approach. So you people, for very big problems, they shouldn't use Verlet. They should use more sophisticated splitting algorithms. So it's not necessary that you accept reject. If you are in accept reject context, then the advantage is that you reject less. But if you are just in a simulation of a molecule or whatever, then by any metric that you use, I don't have time to go into this, those methods really outperform Verlet and can be incorporated into standard codes. When we started this to put this into GROMACS, because GROMACS only offered at the time the Verlet algorithm, I thought that changing to this would be a matter of a few days. And then I asked the people there, in particular this person, Mario, who was then a PhD student, and he took several months for something that I thought would be a matter of days. And this is the reason that this GROMACS is what I later realized that is called spaghetti code. So we think that there's a module that they say, okay, there's the numerical integration, I give you Q naught, P naught, and then there's the subroutine that delivers. No, it's not like this. So starts the integration and maybe changes P, and then writes some information to a disk and retrieves something and so on, and then you have to, well, this guy had to look at all the lines until he found where the next substep of the time stepping were, and then changed it, but then maybe this is interspersed with other metrics and checks and so on. So this is, I have to say that it's also giving them some incentive to write those packages in a more modular form, rather than just suggest to change a module. But anyway, it was doable. he did it, and it was, I think it was really successful. I think this is all I wanted to say.
Thank you. Questions? Yes.
It may be completely, so since it's called Hamiltonian Monte Carlo, so this can be used to compute the distribution because you are modeling the evolution of some sample. But in this problem, sometimes you want to find out the right distribution, right? Or not?
No, you find the right distribution.
So this is what.
But what you find is not the distribution, is not in a piece of paper that tells you f of x, comma, y, z is x squared, y cubed, whatsoever. Is that this gives you samples from the distribution.
Okay. And then you compute the variance.
And then you compute the variance, the mean of various things, correlations, whatever you mean. I mean, this is Monte Carlo. This is what they do. Yeah.
Okay, so when you are solving, when you are actually solving, when you refer to 1 degree of freedom or 2 degree of freedom, those are really samples of distribution.
No.
So a sample of Monte Carlo.
No, those are the variants in the distribution. And then I generate.
Okay.
So if I have a univariate, like the Gaussian, it's 1 degree of freedom. But if I have a bivariate, Gaussian is 2 degrees of freedom. And then regardless of the number of degrees of freedom, maybe I want to generate 10,000 samples or 50,000 samples to find the mean of the distribution, the variance of the distribution, or the expectation of a function of things like that. Okay, and this is essential for Bayesian statistics, because otherwise you don't have any closed form expression. There's no book where you can go and say, what's the variance of my distribution? Because the variance changes with the data that you've gathered from reality. Yeah, so this is.
So you can use to predict the probability that is behind some models.
Yeah. Okay. Yeah. So.
Another?
Can you give an idea of how you done the estimated error in the energy?
Well, it's not difficult. Once you decide to do it, it's not difficult.
Can you give some?
No, you can write down explicitly the maybe. So maybe it was something like this. Maybe not exactly. Maybe. So this is after one step of my method, and those are known functions of the coefficients of the method. And then after n steps, you got an n, and n, like this. Okay, and then you got your initial condition. But your initial condition is a random variable. Okay, so I write this formula that gives me the final state as a function of this random variable. I write the energy of this vector, which is this guy squared plus this guy squared divided by half. Then I've got this as a function of that, and then I use that the average of a sum is the sum of the averages, and for the variance you have to take into account the cross terms, the correlation, and then you do it. And no, it's not a big deal. Once you've thought of it, I mean, once you know that it's interesting, is you do it in 10 minutes.
I think we take it on now first and then Ari.
So just to add to that, I suppose, so essentially you choose the coefficient b and a by minimizing the expected error for Gaussian distribution. Is that and then you apply it to an unknown distribution.
Yeah. Okay. Yeah. So out of this, I get this guy that is known as a function of h, and if I have a family of methods depending on some parameters, so this I will get an expression, and then the parameters that will of them alpha 1, alpha 2, and whatever parameters I have in my family. From this I go to this row that is a half chi minus 1 chi squared. And then maybe it's awful, so if you have a student is better for the student, and then you've got this, and then it's a problem of really finding the maximum in this interval, and then minimizing this, that you do, of course, numerically. Yeah. So in this, what they added to Chromax, there's a module to carry out this optimization each time. So each time the program is run at the beginning, if the program say runs for 3 hours at the beginning, maybe there's 50 seconds, you're solving an optimization to find the coefficients within your family. So this is how it works.
Ari?
So how is the initial guess chosen? Because it seems like obviously you're not going to explore the entire state space if you're just near.
This in practice, what people do is you have the simulation, and you generate the samples, and they divide this artificially into 2 parts. The first part is called the burning, and then there's another part which is called the production part. So for the burning, you start from really any location. In fact, it's better if you have, say, if you have a molecule, you have some idea of what's the likely lengths of the bonds between the atoms or whatsoever. If you are in statistics, you know what are reasonable. And then you start from this, but maybe even you have a good guess. Maybe this guess is at a location of very low probability. It's at the tail of the distribution. So you simulate maybe, I don't know, for 1,000 samples, okay? And the hope is that by obtaining those 1,000 initial samples, you come to a location where you are really more at the typical distribution. So you discard the first 1,000 samples because they would bias your estimates, okay? And then you only use the ones defined. Of course, this is an art, and people have various diagnostics to see whether the burning has been long enough or short, or you need more or you need less. But as with anything else, well, this is the main idea. But then people in statistics write dozens of papers on this to estimate. So say if you had a distribution like this, say you start here. So maybe if you just take a few iterants, you get maybe there, and there. And then if you use those to find the mode of the distribution or the average of the distribution, it's not going to give you a good average, because the algorithm really hasn't seen. So you have to let it go for a while, and then you discard this initial transient phase, and then it goes on and on. And as I said, there are diagnostics that people use to see whether this is really what they call the stationarity of the chain, or you are really in the tails and things are going to change very much.
And is there a similar sort of dark art to deciding exactly how long you run the simulation between to get your proposal?
Yeah, well, this is really I don't know in English, this guy in the Iliad that you could.
Achilles heel.
Yeah, exactly. So this is the whole thing. So this technique compared with other that people use in statistics has a tremendous potential, because you can really have a sample here and then another sample very far away, so that even if you generate not very many samples, they could be correlated, and you could have maybe 3 samples there or 10 there and 1 there with few samples. Whereas if you use more primitive techniques like this random walk, because you don't use any driving dynamics, then maybe you need 1 million steps before you come to this. And those disadvantages become more prominent as the dimensionality of the problem. There are studies on how to scale delta t with the dimensionality of the problem and so on. And so this Hamiltonian Monte Carlo has this big potential. But of course, this Achilles is that it has really several parameters, the delta t and the number of time steps that you take between your initial condition and your final condition. And the performance of the method very much depends on that. And for a general problem, maybe you don't have a clear indication of what are reasonable values of those 2 parameters. So this is a method, in my understanding, that if it's being used by someone who knows about it and has tuned the parameters, can be very, very effective. But it doesn't lend itself very well to be put into a black box that people could use with blind eyes. So this is definitely a big drawback. And I think it's very difficult to make substantial advances there, because it's very difficult for a general ODE to have good estimates of the global error as a function of delta t and your time. This is a notoriously difficult thing. So you really don't have any indication of what's happening there. So this is really what people are trying to consider. If you want to know more, I will just tell you that what one usually does in all these kinds of things is to have all those parameters that you don't are very sure about the parameter, about the values, you just randomize them. So if you delta t, you are not sure if it's 0.1 or 0.2, then you choose it randomly, so that each new application you choose a different, and then you average, and this alleviates quite a lot the difficulties, also the duration. You can take sometimes 20 steps of earlier, sometimes 40, and so on, with a geometric distribution. And then this certainly improves the performance.
So are there situations when the potential is defined on a compact domain and then it blows up on the boundary? So it's some kind of confinement.
Yeah, but you
potential.
Then you can go about this. You can have like a defined potential being infinity, and then you always reject and you are offered.
So this is what I'm thinking. Because if you take a very large step, then you
can
have
do that, and you have to be a bit careful so that you preserve the volume preservation and so on when you discard those things. Or also oftentimes in molecular dynamics, if the molecule is confined, they would put like a wall, stick wall, rather than
infinity. So it's
yeah,
not a virtualizing.
yeah. So there are various things, but you can just have it organized so that it steps out, then you have a rejection. And you have to be careful with the way this operates, so that at the end of the day you have a map that is volume preserving and reversible, even if you step out of the domain. But this is not a big issue. It's just fairly well known, I should think.
Okay, maybe we should we can stop this now, and we can go back to the institute and have a coffee or something.